Introduction to Lw4o6. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are exploring Lw4o6, which stands for lightweight 4over6. This is one of the most sophisticated IPv6 transition mechanisms available, standardized in RFC 7596. Lw4o6 represents an evolution of the DS-Lite architecture we have discussed previously, but with a crucial difference. Instead of centralizing all NAT functionality at the ISP's AFTR device, Lw4o6 distributes the NAT function to customer premises equipment. This architectural shift has profound implications for scalability, performance, and network architecture. The lightweight aspect of the name refers to the fact that the PSID device, called the lwAFTR, has significantly reduced processing requirements compared to a traditional AFTR because it is no longer performing stateful NAT for every customer connection. The fundamental concept behind Lw4o6 is port-restricted IPv4 address sharing, combined with IPv4 and IPv6 tunneling. Each customer is provisioned with a public IPv4 address and a restricted set of port numbers that they are allowed to use. Multiple customers share the same IPv4 address, but with non-overlapping port ranges. For example, Customer A might use ports 2000 through 2999. Customer B gets ports 3000 through 3999, and so on. The customer's equipment, referred to as the lwB4 element, performs NAT locally, translating private addresses on the customer LAN to the assigned public IPv4 address and port range. This creates a deterministic binding between the customer's IPv6 address, their shared IPv4 address, and their allocated port range. What makes this architecture particularly elegant is that the lwAFTR at the ISP edge does not need to maintain per-session state. It simply performs stateless decapsulation and forwarding based on the IPv4 address and port number in the packet. When a packet arrives from the Internet destined for a specific IPv4 address and port, the lwAFTR consults a binding table that maps this combination to the customer's IPv6 address, encapsulates the packet in IPv6, and forwards it to the correct lwB4. This stateless operation means the lwAFTR can handle extremely high packet rates with minimal processing overhead, and it does not suffer from state table exhaustion or the memory requirements that plague carrier-grade NAT implementations. lwB4 element architecture. The lwB4 element is the customer-side component of the Lw4o6 architecture, and it is considerably more sophisticated than the B4 element in DS-Lite. The lwB4 must perform several critical functions. First, it maintains an IPv4 in IPv6 tunnel to the lwAFTR, similar to DS-Lite. Second, it performs network address and port translation, or NAT, for the customer's local network. But unlike traditional NAT, the lwB4 must restrict its source port allocation to only the ports that have been assigned to this specific customer. This port-restricted NAT is the key innovation that allows address sharing without centralized state management. The lwB4 is provisioned with several pieces of configuration data through DHCP-v6 or other provisioning mechanisms. It receives an IPv6 address or prefix for tunnel operation. It is assigned a public IPv4 address that it shares with other customers. Critically, it receives a Port Set Identifier, or PSID, which defines exactly which ports this customer is allowed to use. The PSID is typically encoded as a set of contiguous port ranges, or as an algorithmic specification that determines valid ports. The lwB4 also receives the IPv6 address of the lwAFTR to establish the tunnel endpoint. When a device on the customer LAN initiates an outbound connection, the lwB4 performs NAT translation. It must select a source port from its allocated port range. This requires intelligent port management to avoid exhaustion, while maximizing utilization. The lwB4 replaces the private source IP address with the assigned public IPv4 address and selects an available port from its PSID range. It then encapsulates this translated IPv4 packet inside an IPv6 packet and sends it through the tunnel to the lwAFTR. The lwB4 maintains a NAT state table to track active connections, so it can properly handle return traffic, performing the inverse translation when packets arrive from the lwAFTR. This local NAT state management is crucial. It means the lwAFTR never needs to know about individual connections or maintain per session state. lwAFTR element architecture. The lwAFTR, or Lightweight Address Family Transition Router, is the PSID component that represents a radical departure from traditional carrier-grade NAT architectures. The lwAFTR's primary function is stateless forwarding and encapsulation rather than stateful NAT. This fundamental difference makes the lwAFTR dramatically simpler and more scalable than the AFTR in DS Lite or traditional CGN devices. The lwAFTR maintains a binding table that maps the combination of public IPv4 address and port range to customer IPv6 addresses, but this is static or slowly changing configuration data, not dynamic per session state. When the lwAFTR receives an IPv4 in IPv6 encapsulated packet from a lwB4, it performs decapsulation to extract the IPv4 packet. It then validates that the source IPv4 address and port number match the binding for that particular customer based on their IPv6 source address. This validation prevents customers from using IPv4 addresses or ports that have not been assigned to them, providing a security control against spoofing. If validation passes, the lwAFTR forwards the IPv4 packet to the Internet. This entire process is stateless. The lwAFTR does not need to remember anything about this particular connection or create any session state. For inbound traffic, the process is equally streamlined. When an IPv4 packet arrives from the Internet destined for one of the shared public IPv4 addresses, the lwAFTR examines the destination port number. It consults its binding table to determine which customer's PSID includes this port number. The binding table provides the customer's IPv6 address. The lwAFTR encapsulates the IPv4 packet in an IPv6 header with the customer's IPv6 address as the destination and forwards it through the IPv6 network to the appropriate lwB4. The stateless nature of this operation means the lwAFTR can be implemented with simple forwarding logic. It can be easily scaled horizontally by adding more lwAFTR instances, and it can handle line rate traffic without complex state management or memory bottlenecks. Port Set Identifier and Allocation. The Port Set Identifier, or PSID, is the cornerstone of Lw4o6's ability to share IPv4 addresses without centralized state. Understanding PSID allocation and management is essential to grasping how Lw4o6 achieves its scalability advantages. The PSID defines which subset of the 65,536 available port numbers a particular customer can use. There are several approaches to PSID allocation, each with different characteristics and trade-offs. The most straightforward approach is contiguous port range allocation. With this method, each customer receives a continuous block of port numbers. For example, if we want to share an IPv4 address among 64 customers and we allocate approximately 1,000 ports to each customer, we might assign customer 1 ports 1024 through 2047. Customer 2 gets ports 2048 through 3071, and so on. This approach is simple to implement and easy to understand, but it has limitations. The main issue is that it does not handle well-known ports elegantly. Ports below 1024 are reserved for system services, and many applications expect to use specific port numbers. With contiguous allocation, only one customer per shared IPv4 address would get access to these lower port ranges. A more sophisticated approach uses algorithmic port set distribution based on bit manipulation. This method assigns ports to customers based on mathematical formulas that distribute ports more evenly across the entire port space. The PSID becomes a parameter in an algorithm rather than a simple range. For example, we might use a scheme where the PSID determines which ports are valid based on specific bit positions in the port number. If we have a 4-bit PSID, we could assign ports where bits 10 through 13 of the port number match the PSID value. This distributes ports across the entire range in a deterministic but non-contiguous pattern. Customer with PSID 0 gets ports where those bits are 0000. Customer with PSID 1 gets ports where those bits are 0001, and so forth. This approach provides better distribution and allows every customer to access some low-numbered ports, but it is more complex to implement and requires the lwB4 to calculate valid ports on demand rather than simply checking against range boundaries. The RFC 7597 defines the MAP algorithm, which provides standardized port set calculations that many Lw4o6 implementations follow. Provisioning and configuration. Deploying Lw4o6 requires sophisticated provisioning mechanisms to distribute the necessary configuration parameters to lwB4 elements. The provisioning process is more complex than DS Lite because each customer needs unique binding information, specifically their assigned IPv4 address, PSID, and related parameters. DHCPv6 is the primary mechanism for Lw4o6 provisioning, using options defined in RFC 7598. The DHCPv6 server must maintain a database of customer bindings that associates each customer's IPv6 address with their Lw4o6 parameters. The key DHCPv6 options for Lw4o6 include option S46 rule, which conveys the binding rule including the IPv4 address and PSID parameters. It also includes option S46BR, which provides the lwAFTR's IPv6 address for tunnel establishment, and option S46 port parameters, which defines the port set calculation algorithm and its parameters. When an lwB4 boots up or renews its configuration, it sends a DHCPv6 request that includes its unique identifier. The DHCPv6 server looks up this customer in its database and responds with the appropriate Lw4o6 binding. This binding tells the lwB4 which public IPv4 address it should use, what its PSID is, how to calculate valid ports from the PSID, and where to establish its tunnel. The lightweight AFTR must be configured with the complete binding table that maps all customer bindings. This table contains entries for every active customer, specifying the relationship between IPv6 address, shared IPv4 address, and PSID for a large ISP with hundreds of thousands of customers. This binding table can become substantial, but it is still orders of magnitude smaller than the per session state table that a DS Lite AFTR must maintain. The binding table is relatively static. It only changes when customers are added, removed, or their bindings are modified. This allows the binding table to be efficiently distributed across multiple lightweight AFTR instances or preloaded into high-speed memory. Many implementations store the binding table in a database that multiple lightweight AFTRs can query, or they use route publishing mechanisms to distribute the bindings as routing information that the lightweight AFTRs can use for forwarding decisions. Packet flow and processing. Let's trace a complete packet flow through the Lw4o6 architecture to understand how all the components work together. Consider a customer device on the LAN with private IP address 192.168.1.50 that wants to connect to a web server at public IP address 93.184.216.34 on port 80. The customer's LWB4 has been provisioned with public IPv4 address 203.0.113.10 and PSID 5, which gives them access to ports 5120 through 5375 using a contiguous allocation scheme. The device creates a TCP SYN packet with source address 192.168.1.50 and a random source port, let's say 54321, destined for 93.184.216.34, port 80. This packet arrives at the LWB4, which recognizes it needs to be NATed and forwarded to the Internet. The LWB4 performs NAT translation. It replaces the source IP with its assigned public address 203.0.113.10 and must select a source port from its allocated range. The LWB4 cannot use the original port 54321 because that's outside its PSID range. Instead, it allocates an available port from its range, let's say 5200, and creates a NAT binding that maps the internal connection 192.168.1.50, port 54321, to the external representation 203.0.113.10, port 5200. The LWB4 stores this mapping in its local NAT table. Next, the LWB4 encapsulates the translated IPv4 packet in an IPv6 header. The source IPv6 address is the customer's assigned address, perhaps 2001:db8:1:100:1, and the destination is the lwAFTR's address, say 2001:db8:FFFF:1. The protocol type in the IPv6 header is set to 4 to indicate IPv4 payload. This encapsulated packet travels across the ISP's IPv6-only network to the lwAFTR. The lwAFTR receives the packet, decapsulates it to extract the IPv4 packet, and validates that the source address 203.0.113.10 and source port 5200 are consistent with the binding for source IPv6 address 2001:db8:1:100:1. The validation passes because port 5200 is within PSID 5's allocated range. The lwAFTR then forwards the IPv4 packet to its destination on the Internet. Return traffic follows the reverse path. The server's response arrives at the lwAFTR with destination 203.0.113.10:5200. The lwAFTR looks up which customer owns this port, encapsulates the packet for IPv6 address 2001:db8:1:100:1, and the LWB4 receives it, decapsulates it, looks up the NAT binding, translates it back to 192.168.1.50:54321, and delivers it to the client device. Advantages over DS Lite. Lw4o6 offers several significant advantages over DS Lite, particularly in terms of scalability and performance at the ISP edge. The most profound advantage is the elimination of centralized stateful NAT. In DS Lite, the AFTR must maintain millions of active NAT sessions, tracking every TCP connection and UDP flow for every customer. This creates massive memory requirements, processing overhead for session creation and teardown, and potential bottlenecks during traffic spikes. The AFTR becomes a single point of failure that must handle all IP version 4 traffic for the entire customer base. In Lw4o6, the lwAFTR performs stateless forwarding based on the binding table, which is orders of magnitude smaller than per session state and changes infrequently. The scalability implications are dramatic. And lightweight AFTR can process packets at line rate with simple lookup and encapsulation operations that can be implemented in hardware or optimized software data planes. Adding capacity is straightforward. Deploy additional lightweight AFTR instances and use anycast or load balancing to distribute traffic. There's no complex state synchronization required between lightweight AFTR instances because there's no state to synchronize. If an lightweight AFTR fails, packets can immediately be rerouted to another instance without session disruption because the NAT state is maintained at the customer premises, not in the network. This makes Lw4o6 much more suitable for carrier-scale deployments where handling millions of customers with high availability is essential. From a performance perspective, Lw4o6 also offers benefits. Since NAT processing happens at the customer premises, rather than at a centralized choke point, NAT translation latency does not add to the round-trip time for internet access. The lwAFTR introduces minimal processing delay because it only performs stateless forwarding, rather than complex NAT operations. For latency-sensitive applications, like gaming or real-time communications, this can make a measurable difference. Additionally, the distributed NAT architecture means that NAT processing load scales naturally with the customer base. Each customer's CPE handles their own NAT, so adding customers does not increase processing load at the ISP edge beyond simple packet forwarding. Challenges and limitations. Despite its advantages, Lw4o6 introduces several challenges that must be carefully managed. The most significant challenge is CPE complexity and provisioning. The LWB4 is considerably more complex than a simple B4 element in DS Lite. It must implement port-restricted NAT with awareness of its PSID allocation, manage port selection algorithms, and handle the unique constraints of port set-based address sharing. This complexity means that generic home routers cannot simply enable Lw4o6 support. They need specific firmware that implements the full LWB4 functionality. ISPs must either develop custom firmware, use vendor equipment with proper Lw4o6 support, or deploy specialized CPE. This increases deployment costs and complexity compared to DS Lite. Port exhaustion is another concern that requires careful planning. With Lw4o6, each customer receives a fixed allocation of ports, typically somewhere between 200 and 2,000 ports, depending on the sharing ratio. For most residential customers, this is adequate for normal usage patterns. However, power users or customers running servers, peer-to-peer applications, or other port-intensive services can exhaust their port allocation. When this happens, new outbound connections fail until existing connections close and release ports. The LWB4 must implement fair port allocation policies across devices on the customer LAN to prevent one device from monopolizing the available ports. ISPs must monitor port utilization and potentially offer higher port allocations for customers who need them. Application compatibility issues can arise with port restrictions. Some legacy applications or protocols expect to use specific port numbers or ranges. Network administrators who want to run services on specific ports may find those ports unavailable if they fall outside their PSID allocation. The port randomization behavior that some operating systems use for security can also interact poorly with restricted port ranges. The OS might select a random port that is outside the allowed range, causing connection failures. These issues require careful PSID design to ensure reasonable port distribution and may require application-level workarounds. The deterministic nature of the port mapping also raises potential privacy concerns. An external observer can determine that two connections with the same IPv4 address but different port numbers come from the same customer if they fall within the same PSID range, whereas with random carrier-grade NAT, this correlation is much harder to establish. Real-world implementation. Let's examine how Lw4o6 would be deployed in a production environment. Consider a medium-sized ISP with 100,000 broadband customers transitioning from DS Lite to Lw4o6 to improve scalability and reduce AFTR processing requirements. The ISP has a pool of 400 public IPv4 addresses available for Lw4o6 deployment, which means they need a sharing ratio of 250 customers per IPv4 address. To achieve this, they design a PSID allocation scheme where each customer receives approximately 260 ports. Using the algorithmic approach with a PSID length of 8 bits provides 256 possible PSID values per IPv4 address, which fits their requirements perfectly. The ISP deploys a pair of redundant lwAFTR devices at its internet edge, configured with a binding table that maps all customer assignments. These devices are advertised via Anycast addressing so that customer traffic automatically reaches the nearest available lwAFTR. The lwAFTRs are relatively simple forwarding appliances. They are high-performance routers with Lw4o6 support, rather than the expensive, state-heavy, carrier-grade NAT devices previously used for DS Lite. The binding table contains 100,000 entries, one per customer. This totals less than 10 megabytes of data and easily fits in the lwAFTR's memory for fast lookup. For customer premises equipment, the ISP develops a firmware image based on OpenWRT that implements lwB4 functionality. This firmware is deployed to their standard CPE devices during a phased migration. As each customer's modem reboots with the new firmware, it performs DHCPv6 configuration and receives its Lw4o6 binding, an IPv4 address, PSID, and lwAFTR address. The lwB4 calculates its valid port range from the PSID and begins operation. From the customer's perspective, nothing changes. Their devices continue to work exactly as before. The ISP monitors port utilization metrics to ensure customers have adequate port allocations, tracking metrics like average ports used per customer, peak port usage, and port exhaustion events. Over 6 months, they complete the migration of all customers from DS Lite to Lw4o6. The operational impact is significant. They can decommission their expensive carrier-grade NAT devices. The lwAFTR devices show CPU utilization below 20% even during peak hours, and they have eliminated the periodic AFTR state table exhaustion issues that plagued their DS Lite deployment. Future and evolution. As we look toward the future of Lw4o6 and IPv6 transition technologies more broadly, several trends are emerging. Lw4o6 represents the current state-of-the-art for ISPs that need to support IPv4 services while operating IPv6-only infrastructure with maximum scalability. The technology is particularly well-suited for environments where the ISP controls the CPE and can ensure proper lwB4 implementation. We are seeing increased adoption in carrier and enterprise networks, particularly in regions where IPv4 address scarcity is most acute and where ISPs have already deployed DS Lite and are looking for the next evolution. The relationship between Lw4o6 and other transition technologies continues to evolve. Some ISPs are deploying hybrid approaches using DS Lite for legacy customers with older CPE that can't support lwB4 functionality, while migrating customers with newer equipment to Lw4o6 to reduce load on the centralized AFTR in mobile networks. 464XLAT remains dominant due to its integration with mobile operating systems, but Lw4o6 is seeing adoption for fixed wireless and home broadband over cellular connections where the carrier can control the CPE. The MAP-E and MAP-T variants specified in RFC 7597 and RFC 7599 provide alternative approaches to the port mapping algorithms while maintaining the same architectural principles as Lw4o6. Looking further ahead, Lw4o6 will likely remain relevant throughout the extended IPv6 transition period. While IPv6 adoption continues to grow, IPv4 services will persist for decades to come due to legacy systems, older applications, and the massive installed base of IPv4-only devices and infrastructure. Lw4o6 provides a sustainable way to support these IPv4 requirements with minimal ISP infrastructure and maximum scalability. The stateless architecture aligns well with modern network design principles of pushing complexity to the edge and keeping the core simple and fast. As software-defined networking and network function virtualization become more prevalent, the lightweight nature of the lwAFTR makes it an ideal candidate for virtualized or containerized deployment. We may see lwAFTR functionality implemented as a microservice that can be dynamically instantiated and scaled based on demand. The binding table could be stored in distributed databases or blockchain-like structures for enhanced reliability and auditability. Whatever the future holds, Lw4o6 has established itself as a mature, scalable solution for the ongoing challenge of IPv4 service continuity in an IPv6 world. Thank you for your attendance. Please consider subscribing to the channel.